Welcome back, everyone. So we're now on week 6 of 16. So definitely getting through it. Before we start our work for today, any questions folks would like to start us out with? Okay. Oh, sorry, go ahead.
Number 35.
Sure. 3.5, number 35. Let's take a look. Oh, so this was the lemniscate kind of problem. What was your question on this one? Kind of getting started or just working through the algebra part of it, you're saying?
Yeah.
Gotcha. Yeah, this one's kind of a tricky looking one. Let's give this a try to start us out. So I'm going to take this. And just a reminder, if there's a question from class to start us out, I always appreciate it. And I usually put it on the notes of the day. So let's put it right here. And this information will start on page 2. Okay, so thanks for starting us out with the question on this one. It says use implicit differentiation to find the equation of the tangent line to the curve at the given point. So here's the point we're going to do. We want a full-on equation line, which means the major thing we want is the slope. All we know is that it's negative, but that's good information. If we make a silly algebra mistake, we might be able to detect it if we got like a 0 or a positive slope. So doing this much just kind of lets our subconscious chew on the problem, lets us get started. And the first thing we have to decide is, do we want to clean up the function or just differentiate it as it stands? I'll leave it up to the folks. With a power 2 there and a coefficient of 2, we could square it and expand it, distribute 2 through. Same with the 25. Or we could just differentiate in this form. Any volunteers for which way to go? If you multiply it in, it would have to convert to a 4 in order to go inside because of that power 2 right there. Gotcha. Let's try out expanding it by, say, let's go 2. Expand this right out. We'll go x squared plus y squared multiplying itself. The right-hand side is 25 x squared minus y squared. And if we were to expand this out, let's keep that 2 parked here. I'll just do another set of parentheses. We'll get x power 4 first as we start to multiply. Then when we multiply here to here, we'll get x squared y squared. We get it again here to here. So I'll just say 2x squared y squared. Adding it on, 2x squared y squared. Finally, y power 4. The right-hand side, we have 25 x squared minus 25 y squared. So we could leave that 2 there, but we might as well keep going, right? It's not a bad idea to clean it up just to make it nicer to differentiate to start out. So if we distribute that through, we have 2x power 4 plus 4x squared y squared plus 2y to the power 4. On the right-hand side, nothing's happening as of yet. It's 25x squared minus 25y squared. And this is all just the pre-algebra portion, or the pre-do the algebra, and then the calculus, not actual pre-algebra. That was a weird way to say it. Now we are ready to differentiate both sides. What I would do with that is definitely make the derivative portion pop out. You can either put a d by dx on the left-hand side here if you like, or you can just put a prime on that entire group to say, now we're differentiating. Then going term by term, first we use the power rule, 4 comes down and we get 8. Let me change the color back to black. 8x cubed. So that's a nice derivative. Then when we go over here, now it's suddenly not so nice. Anyone see what the rule we would have to use by the red dot would be? Good call. That's a product rule right there when it's being multiplied. And it's even worse. That's a product rule together with the chain rule, because when you see the y, that's not a variable. Y is a function of x. Let's put this over to the right just as a reminder. Y is equal to f of x, so we have an implicit function there. Now when you look at y squared, y is the inner function, power 2 is the outer function. So we have to be careful as we differentiate that. The product rule comes in, so I'm gonna go plus. Try to remember my primes. It's always a bad thing to forget there. Let me highlight them in yellow. Then we'll have 4x squared, y squared, 4x squared, y squared. So that navigates us through the product rule on that one, and we'll just come back to that term on the next step. Now we differentiate right here next. This one is implicit differentiation, so the chain rule is still in play. I'm going to put these zeros here just as a temporary guidance. I'll delete them so it doesn't get too busy. That 4 is the outer function. And the y right here is the inner function. Maybe we can leave those arrows stay, that kind of fits. So the first thing is we take the derivative of the power 4 function. 4 will come down multiplying the 2, so we'll have plus 2 by 4. Then the new power of y is 3. But because this is implicit differentiation, we now multiply by the derivative of the inner function, which is y. So go times either a y prime or dy dx, your choice. So that's the entire left-hand side. Copy equality. And then we just do it again on the right-hand side. Any questions to that stage so far? Okay, so differentiating over here. This one's not too bad, it's just x. So 2 comes down and multiplies. This will be 50 x power 1. And this one's not as nice. This one, well, first 2 will come down and multiply 25, so it's negative 50. Then the power on y is still y power 1. But every time you multiply, or excuse me, differentiate around y, you get times dy dx through implicit differentiation. So that was differentiating 2. That's why the 2 came down, multiplying to get 50, u power is 1. But then we take the derivative of what's inside, and that's the dy dx right here. Or I notice I have a prime. No, I did go dy dx on that one. So it's getting messy, but we're getting through the actual calculus portions. Any questions to this stage? Okay, on the next step, this will become 8x cubed. Then this is not too bad. This will become 8xy squared. So the 8x is just differentiating the 4x squared there. And then y squared copies in. Here, this will be plus 4x squared. Then we differentiate this thing again, the y squared. 2 comes down. New power of y is 1, so I'll just leave it as a y. Then we multiply by dy dx. So that takes us through to here. Now we're pretty much just copying. I'll change that to plus 8 y cubed times dy dx equals 50x minus 50y times dy dx. So now it's fully expanded. I think we've done all of our derivatives. Does everything look all right to everyone so far? Okay, next step is, let's put it here. Next, solve for dy dx. That'll give us our derivative. Put 3 for x, 1 for y inside your answer. You'll get your slope. And then do the standard thing to get the actual tangent line equation. I'll leave the rest of the steps for the folks here. But if you have questions on this one, don't hesitate to ask again. I'll be happy to return to this problem. Any questions at all on this one here? Okay. Again, I think what's tricky about this problem is all the extra factoring right here. If they would have expanded it all out for us, it would have just been easier to differentiate on site and not worry about it. But I think the reason the author sometimes does it this way is it might just be the form of a lemniscate, or he wants us to practice putting things into a better form for differentiation. Well, that was our warm-up problem for the day. Other questions or comments so far, folks? Okay, thanks for asking about that one. Well, we're now in section 3.6, dealing with logarithmic functions. And on the Moodle website here, for the upcoming assignment number 6 to be officially posted Thursday, it'll only be 2 sections. 3.7 is our application section in chapter 3. So we'll take a little bit extra time getting through that one. thinking about doing about a day and a half on both of these sections. And on this section here, it looks like a lot of problems, but these are the fast, just differentiate and move on. So that's not as bad as it looks. But watch out for this right here. There's a big hint on these problems. It's not as if every single problem you'll use this hint, but if the calculus looks a little bit nastier than normal, if you feel like I'm going to take 30 steps in algebra just to simplify this, it wasn't meant to be that hard. Probably you just didn't use properties of logarithms, which can get us through the problem really fast. To get the properties of logarithms, you can open up this document, Logarithms Review Material. It gives us a lot of stuff you might want to know about logarithms. They're the inverse of the exponential function. But go down to the bottom, and this is the stuff that I'd probably be using. I did assign in the past a problem that eventually used the change of base formula that you didn't have to do, but someone in the back of the book did. That's the only reason this is here. I think I unassigned it this time though, but there might be a cost to using change of base formula, never on an exam setting. I think that'd be kind of inappropriate. But these things are something we have to be ready for anytime they come up, especially for just dealing with logarithmic type functions. So let's take these. I'll put them on the notes, and anytime we have cost to use them, we'll highlight our use of it. So I'm just going to kind of move the screenshot down as we go through the notes. Okay, so we're taking derivatives of logarithmic functions. Really, the first thing that has to happen then is a theorem should tell us what is the derivative of a logarithmic function. And here it is. The derivative of log base a of x is 1 over x times the natural log of a. If you happen to deal with the natural logarithm, the derivative of the natural log of x is 1 over x, an even nicer derivative. And let's put down a couple more formulas. If you had y equals a to the x, just as a reminder, the derivative of the exponential function, which is inverse to log base a, would go like this. Y prime is a to the x times the natural log of a. Notice for log base a of x, you get 1 over x times natural log a. It's just kind of baked into the problem, whether it's the exponential or the logarithm. But if our function for the second row, matching up with this one, natural log x has inverse function, e to the x, they're inverse to each other, and the derivative, y prime, is itself e to the x. It's not e to the x natural log e because natural log e is 1. And that's really this property right here. Let me see if I have a better property there. Yeah, it would be really this property. Natural log e is 1, and that's because natural log of e is really log base e of e, and that's property number 1. There's a cancellation going this way, leaving just the exponent of 1 itself. Well, those are our two formulas. Any questions at all, folks, about either one of them? Okay, they're great formulas, especially this one right here. If you're differentiating the natural log, all you do is you take your x, throw it into the denominator, and you're in really great shape. There's another one that's even similar to that. Let me put it on the side. You differentiate with respect to x, the square root of x, it becomes 1 over 2 root x. That's a formula we discussed last class and used in a particular problem. So certain derivatives are just kind of nice, especially when you notice the pattern. The root x becomes 1 over twice root x. Natural log x is just 1 over x. But before we go and start working with this, I feel like these do need some explanation on just why they work, because they're kind of surprising derivatives. So I'll leave it up to the class. Let's do a derivation. We'll be practicing properties of logarithms and implicit differentiation. But my question to you is, which one would you like to derive? The natural log formula or the log base a formula? Top one? Awesome, good choice. That's the harder one. Let's do the natural log base a. That's really not too hard, honestly. Anytime there's a base a where it's not e, there's just a little bit of extra information like we see here. So let's derive that formula. That's a good choice because if you derive that formula, you've also proven the one down below. It's just a specific case where the base is e. So here's how it goes. We need to just grab a function. plot y equals log base A of X. Automatically, A is positive and it cannot be 1, or a logarithm function makes no sense. Now that we have that function, we need to differentiate it. And that's where I get stuck, because I can't just differentiate the left-hand side. Differentiating the right-hand side would be using the formula, but that's what we're trying to show. We can't use it. That's okay. Here's our big trick on this one. Whatever the base is of your logarithm, I want to make it the base of the left-hand side. So now it's a to the power of y equals whatever I do to the left side, we have to do to the right-hand side. So now a is the base of the right-hand side. So it's a to the power of log of the base of a of x. Takes a while to even say that, but that's how it starts so far. Any questions to this stage at the moment, folks? Okay, different way to say it is, if you have equality and your bases are the same on the left and the right, the exponents must be the same. So it doesn't matter if you start with equal exponents going up, down, or down, up. You would have both nice equations. And here's where this property comes into play. Properties 1 and 2 are just facts that an exponential and a log to the same base, they're inverse to each other. So if it's written this way, log base b and b will cancel, just giving you an x. And if it's written this way by the red dot, that's what's going on right here. New cancellation, and we get back an x, which is much easier to work with. So now we have a to the power y equals just x by property number 2. Any questions to that stage so far? Okay, this is pretty much like our warm-up problem at this stage. Here, we can differentiate where the red dot is because we have this formula right here where the red dot moved to. We can differentiate a base A function that's exponential. What we couldn't have differentiated was this. That had to be proven. So on the left-hand side, I'm going to go like this. Put a little prime symbol to say we're differentiating. We'll do it again on the right-hand side. And this is purely just implicit differentiation on this row. We happen to know what y is. It's log base A of x. And so when you see a to the power y, it's the chain rule once again. The inner function is y. So we'll handle it second when we go to use our chain rule. And the a to the any power function, that's the outer function, we'll handle first. So y, which is log base A of x, went inside the a to the power of x function specified here. So now through the chain rule, let's hide the properties for the moment. We'll have on the left-hand side, derivative of the base a goes like this. A to an input multiplied by the natural log of a. Now that's the whole use of this formula right here that we cited at the start of the notes. The thing that's going inside, oh, sorry, I did miss one tiny thing. If I take the derivative of the outer function, that's what it looks like. But then we go times something else who will be differentiated. So that will be the formula of just using chain rule. Thing going inside is this function y. I'll go here and right here. Any questions, folks, to that stage? Okay, so this portion right here, that's just the formula in that location. The thing I almost sped through and missed was because it's a chain rule, you multiply by the derivative of the inner function. So there it is right there. That's how the left-hand side goes. The right-hand side is not so bad. Derivative of x is 1. X is not a function of some other variable, so it's an ordinary differentiation formula. So that's how it stands. This y prime, you can just leave it at y prime, or you could call it a dy dx. But we now have a to the power of y times the natural log of a times dy dx is 1. That means you can solve for dy dx. You're just dividing by a to the power of y times natural log a. Let me just carry that up and do the division step here, so we're not scrolling and zooming out so often. Dy dx is now equal to 1 over a to the power of y times the natural log of a. And that's our derivative, except that doesn't look like that just yet, right? We still have a mismatch, but we used implicit differentiation. We differentiated using formulas we know to be true. We solved for dy dx, so the derivative is isolated. But now the trouble is, if you said dy dx, you want your right-hand side to only involve the variable x. You want to eliminate the variable y. So that's the last thing we have to do. Eliminate that y right there. Any questions so far, folks, before we go to make that substitution? Okay, that's going to be our next step. We'll say dy dx is equal to 1 over a to the power of y. But y comes in this new fashion. Y is just as good as a log base a of x. Then here's the natural log a, also copied in. Once we have this, it's another cancellation. Let me scroll down to the properties or bring them up. We're looking at, let's see, base a raised to the power of log base a of x. That's property number 1. We get an immediate cancellation, and the only survivor there is that x. Again, that's what it means for the functions to be inverse of each other. Whatever the exponential base a has done, log base a will invert it, and you just get your x right back. Let's scroll up to the top then. That means our answer, once we simplified, is equal to 1 over x, the natural log of a. And that finally proves that formula right there. Again, it's a weird formula because all we had to do was use implicit differentiation right at this step right here. Then we use properties of logarithms to simplify and get right to our form. If it's dy dx, our answer should only involve x. And again, that's kind of a nice derivative. You just have to remember the natural log of a if it's log base a. If it's natural log, the wonderful thing is the natural log of e is 1, and so the formula simplifies massively. Well, we've got it, folks. That's our new thing that we're going to be getting through today. These notes are a little bit longer. Here are our 2 new derivatives, but essentially, this is an application of implicit differentiation. Implicit differentiation allows you to take a function like a to the x and use known derivative for a to the x to differentiate its inverse function, log base a of x. There's a huge ramification for that, and this is it. When we come back on Wednesday's class, we'll be doing half a day going through these derivatives here, and then we'll go to the next section, 3.7. These were supplied. This is section 3.3, derivatives of the trig functions. But every one of those, if you restrict the domain to the right set of numbers, is a one-to-one function, which means they can all be inverted on the right domain. And here are their derivatives of the inverses. That's not the nicest table ever, right? But it is what it is. We'll derive the one for cosine to see how it goes. But that's a consequence of implicit differentiation. Now we can differentiate all the inverse functions that we would like to. But before we get to that stuff, let's still focus on the fun stuff here, the logarithms. Any questions, folks, before we practice some of these? Okay, let me take this right here. And again, they're just going to walk all over the notes and finally settle somewhere on the bottom when we're done using them. But you can find them on the Moodle file as well that we were looking at. So example 1 says compute the derivatives of the following functions. I think I forgot the functions that are written down here as well. The 2 functions we want to differentiate will be f of x equals the natural logarithm of x squared. And the next function is g of x equals the natural log of x times sine x. The way I wrote these on the document here are about how they'd be typesetted in your actual textbook. More often than not, these functions are written in this way. But if you're going to do calculus on them, sometimes it's not a bad idea to change the notation. Now, let me show you what I mean by that. We'll do both of these. I'll start with the f of x function, but I want to write f of x in this way. F of x is natural log of x squared. The extra parenthesis, although not mandatory, it's truly helpful. It's going to help us to determine which properties of logarithms could we use if we so chose to. Nothing stopping you from differentiating this right now. You would use the chain rule. Sorry, say again. Oh, my bad. We could use the chain rule to differentiate this right now. The properties of logarithms can get us out of the chain rule and make the derivative much, much faster. In some cases, it's the difference between a 2-minute problem and a half-an-hour problem if you're showing all the steps to get through it. Will anyone see which property we can use on this? The hint is really, that's right there. That power is kind of exciting anytime you're dealing with logarithms. You can move that power. And the way it goes is right here on property 7. Any power on your variable, as long as that variable is inside the logarithm function, can turn into a coefficient. If you take that step, you've eliminated the chain rule completely, and this derivative becomes much, much nicer. So let's write our function as f of x equals 2 natural log x. Now that's going to be a lot easier to differentiate. This is just the constant multiple rule. We differentiate f right here. Let's call it f prime at x. We'll get 2 times the derivative of natural log x, but that derivative is just a 1 over x. So you get 2 over x, and now the whole problem is over. If you did the chain rule on this, you would get the same exact result. It just takes more steps. But I'll leave it up to the class. Should we do that just to see what happens? Did I hear yay or nay? Sorry. Yes, awesome. Let's do it. Let's differentiate this with the chain rule and just see what happens to it. I mean, that'd be a really good sell on why you want properties of logarithms. Truly, this section 3.6, it's half algebra, half calculus, really, when you're dealing with logarithms. The half algebra is knowing those properties and using them correctly. We don't use them on this one, not too bad of a deal. We have f of x equals natural log x squared. In this write-up, we would call the x squared function, all of it, that's the inner portion. Then natural log of x, that would be the outer. And so upon differentiation, here's what happens to this thing. F prime at x will become, differentiate the outer function first. What the natural log always does is it produces a 1 in the numerator and throws your input down below into a denominator. And as per chain rule, we multiply by the derivative of that input. The input itself is x squared, so that means x squared goes here and here all at once. Then it's just about done. We can copy our x squared to the denominator. This x squared, which is being differentiated, is multiplying inside the numerator. So I'm just going to write it in right here. Derivative of x squared is 2x. Then we can reduce. 2x divided by x squared becomes 2 over x, matching up with this right here. So honestly, the chain rule wasn't too bad, right? But it is more effort, and properties of logarithms don't just get you out of chain rules, they get you out of a whole lot more. So we'll try to emphasize the better strategies on each one of these problems that we try to do. I'll put a box here to say that that's our official computation here, and this was just practice with chain rule. Any questions either way we did it? Okay, now let's try this again. So if our author typeset this and put it in our textbook, that's probably how the function would look like. G of x is natural log x times sine x. But to me, if I were to write this out personally, and I wanted to emphasize which rule I'm using, I would write it this way. G of x equals the natural log of x, and then close the input around x to say nothing else is going in, times sine x. And notice this is really kind of nasty in a way. I'm going to delete this in a moment, but if g of x was written as natural log sine x, that's a completely different function. What they would have meant here is g of x is the natural log of input sine x. But down here, if there's an X here and an X here, that's a product rule. Whereas up here, this one is a chain rule. It's just missing the X. That's the only thing that's deciding between product rule and chain rule on these things. Really kind of nasty. So it's always good, once again, look before you leap, because the format of how this was written is really has a lot of ramifications. Parentheses help because I can't put parentheses around nothing. And if I put parentheses like this, that's more clearly a chain rule. Well, let's go ahead and differentiate this thing. If it's product rule, I'll think of it in these terms. Now let's go to differentiate this thing. G prime of X. What you could do is put down those 4 parentheses like we typically do. You know what? Let's do that. We're still kind of warming up. It's only 30 minutes in. The product rule will always go like this. Then I'll put natural log X in the first slots, and then sine X in the second slots. Here, notice I'm not saying natural log of X. I dropped those parentheses. I really just wanted them up here to emphasize to my eyes primarily that that's product rule. Here, it was less of an issue. Now we're just about done. G prime at X, once we calculate, first is the derivative of 1 over X. Anyone recall what happens here? What happens to, sorry, say again?
1 over.
Exactly, that one turns into a 1 over X. Copy in our sine X. I want to change that to black just to say no derivative happened there. Plus, here we'll copy in natural log X. I'll put a parentheses around that to say, now when we differentiate sine, nothing over here is going inside that logarithm function, but the derivative of sine X will go to cosine of X. Well, that's pretty much it. There's not much I can do to simplify this thing. I mean, you could call it sine X divided by X instead of multiplying by 1 over X, but that's just a stylistic choice. It's the same thing either way. That's the derivative of this one right here. Again, it's kind of subtle because this is really easy to miss. They were trying to say product rule, whereas if it was written here, this one would have been chain rule. Well, let's put a note here just to emphasize what was going on with that. Chain rules, that's true, but let's call it chain rule. There we go. Well, that's 2 fast derivatives. Really, the punchline with these derivatives are the format of the function can change whether it's a chain rule or not. And even if it's a chain rule, properties of logarithms can slip right past it. Properties of logarithms can sometimes reduce a lot of different things, like potentially even a product rule. But any questions, folks, on getting through this one? I think I said that already. Let's try a harder one. How's that sound? So the way these get hard is not at first too bad. What they might try for a harder problem is just to throw a lot of stuff at us. So here's what it could look like. So something that looks awful at face value could go like this. For part A, let's let y equal 5x to the power 7 minus 13x squared plus 9x minus e. Why not? Let's just throw an e on there because we can. So there's our function. And I'm missing one extra thing in front of that. I mean, that would have been a nice derivative, but let's say it's y equals the natural log of all of that. Sorry, I forgot this natural log right there. So for differentiating that function, we just need to know what the natural log does, because that natural log, that's going to be our outer function. All of this stuff inside, that'll be the inner function. So here's how the derivative will go on this. First, I would say the bigger thing to take a look at here is that there is no property of logarithms for this. And why is that? It's because all the terms inside are separated by pluses and minuses. And I noticed that 9 looks weird. It's really a 9. There we go. Everything that's separated in pluses and minuses, well, there's nothing about that. Property 5 is multiplication. This is division. And property 7 is exponentiation. The pluses and minuses are if the logarithms are attached to each one of those portions. Here it's not, so you can't do anything to simplify this. we'll just go right to the derivative immediately. Let's call it dy dx. And here's how it's always going to go. First, let me fix my numbering here. Let me put this in red. I got my order backwards. I need to do that one first. Sorry, I switched that and that 1 second. They should go 1 and 2. 1 is outer, 2 is inner. Then the derivative of the outer function goes like this. Done. Then the chain rule says multiply by whatever went there. And now that portion is done. Inside both of those placeholders, we just produce that inner function. So 5x power 7 minus 13x squared plus 9x minus e goes right inside here. Then here as well. So we always copy twice. 5x power 7 minus 13x squared plus 9x, and I need a little bit more space, minus e, and then there's our prime. So there it is. We just need to differentiate this. The denominator is going to remain unchanging. 5x power 7 minus 13x squared plus 9x minus e. Then when we differentiate this whole thing, we can multiply up into the numerator and just copy in the result right here. So here, with the power function, we'll get 35x power 6. Moving over, it's another power function, so minus 26 times x. Here, if you differentiate 9x, you get a 9. So here's plus 9. And the derivative of e, because it's constant, it just vanishes, goes to a 0. And that means we're done. That's finally the answer. It looks nasty, but here's all that really happened. We took the inner portion, copied it in right into the denominator, because the derivative of a natural log goes 1 over x. Then, because all this stuff is not just x, we had to multiply by its derivative, and we just multiplied it up into the numerator. So there's where it went. So even though it looks kind of nasty, these are the nice ones. They go really, really fast in practice. Any questions at all, folks, on getting through this one? Okay, next one is not as fast, but let's give it a try. So part B, and I want to copy this down as well, just for emphasis. Let's find a good color. That looks pretty poppy, I think. So that's our big hint on our next one we're going to try. And the function this time goes f of x equals natural log of 3x e to this power of the square root of 7x. So it's for problems like these that you're seeing the notes in Moodle from the homework, this statement, hint, use properties of logarithms. When you go to differentiate this thing, it does do what part A does. All of this stuff would go to a denominator, but then we need to multiply by the derivative of all this stuff. That would be a product rule. You have to show the steps of all that to get credit. And it is a lot of work to do all that. It's not too hard to make the work even worse on these. There's a couple that are a little bit worse than this one. We'll give it a try. So our goal on this one is we're going to do some properties of logarithm surgery on it first, then we'll differentiate. And the big ones are always these last three are good ones for simplifying right before you differentiate. So it's either going to be properties 5, 6, or 7, or some combination, or maybe every single one of those ought to be used until it's simplified as much as feasibly possible. So I'll go to blue where we go to simplify, and then I'll go to green because that's already highlighted. Then we'll differentiate it in blue. So it's still f of x. Anyone see which property we should use amongst 5, 6, and 7 to start? Good call. If we have a bunch of things being multiplied together, we really should start with property number 5. Property number 5 has 2 factors. We have 3 factors, and so we can do it like this. If everything's being multiplied, a logarithm converts multiplications into repeated additions. So this turns into natural log of 3 plus natural log of x plus natural log of e to the power of the square root of 7x. So that's already a huge simplification. The derivative of natural log 3, that just goes to a 0 because that's a constant. This one will turn into 1 over x. That was our formula at the top. And this one, I wouldn't want to differentiate at all. We could still use properties on this thing. Anyone see what properties we need for that? I agree, property number 7 does the job. The reason we want property 7 is that's an exponent. It doesn't have to be an exponent like 5. It could be an entire function like cosine x, for example, or tangent x, or just root 7x. But whatever is there, it becomes a coefficient by property 7. So that's huge for us. That means if we drop that down, we can say f of x is natural log 3 plus natural log x plus the root of 7x times the natural logarithm of e. So that's our big step right here on property number 7. And it gets even better because if you see natural log of e, anyone know what that would be equal to? Not quite 0, but you're on the right track. It reduces very, very nicely. It'd be 1, exactly. That's really property number 2, but it's just disguised. When you see natural log e, think of log base e of e to the power 1. If that's a 1 there, you would get 1 as an output. In other words, that's just an immediate cancellation because it's multiplying. And we're in business with this. We're now ready to run through it and differentiate. Let me just write it down one more time. F of x is natural log 3 plus the natural log of x plus the root of 7x. So this one would have been a chain rule into a product rule into a chain rule. We've reduced that to the sum rule and one chain rule situation. That's not too bad. Any questions at all, folks, before we now differentiate the thing? Okay, so with this function in that exciting format, we get an answer that goes f prime at x equals, to me, the first term is the trickiest one. That is a constant, it must go to 0. Natural log 3, it's got to be just a little bit less than e itself, but some kind of positive quantity. So we move over to this one. The formula is derivative of natural log x becomes 1 over x. So that one's done. Then here, that one is a chain rule, but there's also a nice shorthand formula for this. We did it off the top of the notes, and it goes like this. Every time you differentiate a square root, you get 1 over 2 times the square root of something. Through the chain rule, we multiply by the derivative of that something. That something is 7x. So now we just need to crank out that last derivative right here. The whole answer for the derivative is 1 over x plus 2 over root 7x. Finally, the derivative here is just going to give us a 7. Yeah, go ahead. This one right here, that one went to 0 because it's a constant. E is a constant as well, yes. Natural log of e is 1. Yeah, that would be the value for that as a constant. It would be the constant of exactly 1. Does that make sense there? Gotcha. Other questions at the moment? Okay. Well, that one is honestly not terrible if you didn't use properties of logarithms, but it does take a lot of work to get through. Your answer is not going to look like this. You're going to have a fraction where the least common denominator is produced. It's all added together. And so it typically looks a little bit worse than what these answers are looking like. Well, let's try this again. Any questions at all so far? Okay, so here's our part C next. We did one where we used property number 5 a whole bunch. So let's do one where we have to use property number 6. There's a division that comes into play. We'll call this one part C. And this one goes Z, because it could be any letter we want. That's always kind of weird, but the independent variable is Z, which is equal to log base 7. Now it's getting weirder, but it's just a different logarithm. It's going to work essentially the same way. The input is t for time. It's not an applied problem, but applied problems could be written in this way. Times the root of 7t minus 4. That's 7t, not 70. I don't like t as a variable. It has all sorts of issues. And then the denominator is t to the power 5 plus 3 raised to the power of 4. So that's our function that we must differentiate. Let me see if I can put it on the new page. Now, this is one where if you have a lot of time, I wouldn't submit this for homework, but if you have a lot of time and you're just bored, try differentiating this one directly without using any properties of logarithms and see if you can get the same answer. It's a wild adventure in algebra. It takes a lot of erasing and trying again, but it's another good sell on why this is so important. Without properties of logarithms, this is easily like a half-hour problem, maybe longer if we make mistakes and have to try again. But instead of doing all that, here's what we're going to do. The moment you see a division bar, you really want to use property 6. There's also multiplication right here, so we also want to use property 5. But things are being raised to the power, like that power 4, or that square root, which is a power 1/2. We really ought to use property number 7 as well. And a common mistake with this kind of problem is only using property 6, or only using 5 and 6. I mean, that's good, but you're still working extra hard if you don't use all 3 properties. So for each problem, try to find a way to simplify as much as possible, not just a little. So here's what our answer is going to look like. Either call it z prime, or let's give Leibniz notation some love. It's the derivative of z with respect to the variable t. Oh, geez, I shouldn't have written that. I wanted to do one other thing first. I think I just had a micro sleep there. Before I go to that derivative, we're going to use properties of logarithms. So I should just say z equals, I just got excited to differentiate it, I guess. And now start using the properties. I'm going to start off with property number 6. Handle the division there. And this is what it will look like. Log base 7 of t times the square root of 7t minus 4. I'm going to eventually convert that square root to a power of 1/2, but we can leave it like that for now. Now there's a minus. Divisions become subtractions in logarithms. And we take log base 7 of the denominator. I think I'll keep brackets for that still. T power 5 plus 3 raised to power 4. So that takes care of property number 6. There's no more quotients to worry about. But we still have property number 5 right here. We can split that up into 2 more logarithms, which is a good idea. And for this right here, we can use property number 7 and let that coefficient 4 come down. Excuse me, let that exponent 4 come down as a coefficient. We didn't do that. This right here is still a pretty wild adventure because there's an outer function, there's an inner function, the power 4, and then there's an innermost function, t power 5 plus 3. That's a chain rule with 3 functions if we let it sit just as it is. Okay, so on our next step, here's what we're going to do. That multiplication is going to split into addition. So it's log base 7 of t plus log base 7 of, instead of the square root, let's put in the power of 1/2. 7t minus 4 to the 1/2 power. Okay, we're done with that portion. Then there's a minus. And we might as well move that 4 down right now. 4 log base 7 of t power 5 plus 3. Now that one's done, and we're in much, much better shape. Any questions so far, folks? Okay, with the way it stands, this is still a hard function to differentiate, which could be made quite a bit easier, significantly easier, if we use property number 7 one more time. And the place we use it is right here. That 1/2 can also carry down and become a coefficient. So z, once and for all, in its best form for differentiation is log base 7 of t plus, let's move that 1/2 down, 1/2 times log base 7 of 7t minus 4. Now, again, this always deserves reminding. The moment you see a plus right here in algebra, that's not a good sign. It means there's no simplification for that logarithm. If it was a square root, it's the same problem. Essentially, additions mess up this kind of work in algebra. They make things a little bit harder. We just have to carry that function exactly as it is. So minus 4 log base 7 of t power 5 plus 3. We did it, folks. That's the walkthrough on the properties of logarithms. I think I was trying to erase it. There we go. Now we're ready to differentiate. Before we differentiate, were there any questions at the moment? Okay. Let's put down just a couple really fast formulas for reminders. The derivative with respect to x of natural log x is wonderful. Just a 1 over x, a very fast derivative. But if you have a different logarithm, maybe it's log base a of x, this becomes 1 over x times the natural log of a. That's the one we derived with implicit differentiation. So that's the formula we have to use. For us, this a value is the 7 right here. So let's go and differentiate. The derivative of z with respect to t, now is an appropriate time to write that in, goes like this. We're just going to go left to right and differentiate as we see them. First, it's log base 7 of t. This will be 1 over t times the natural log of 7. And that's this formula right here. Does that make sense to folks so far? Awesome. Then we do it again, but as we do it again, this one is a chain rule. Let me show you how I probably do this one. 1/2 is a constant multiplying. So the constant multiple rule says go plus 1/2 and multiply by. Now it's the derivative of this thing. It's going to take all of its input, put it down below, and multiply by natural log of 7. Then we multiply by the derivative of that input, and it would look like this to start out. So the input is 17 minus 4 down below. And it'll go here as well, where we'll differentiate it on the next run through. Now, some people, I mentioned this before, but if you feel like you've done the chain rule a lot and you're getting pretty fluent with it, you might have wrote the 1/2, 17 minus 4, natural log 7, and then just differentiate that and throw it into the numerator. If that's okay with you, then that's not a bad shorthand to take for these kind of problems. But we haven't done chain rule for a lot, so I'll be careful with these as we go. Next, it's minus 4. It's another logarithm, so this one will go times. I'm running out of space, so let me just try to make this fit. 1 over something times natural log of 7 times the derivative. Oh geez, that's not going to fit. One more try. I think I can get this in there. Always is weird to run out of the edge of the paper on a computer. So minus 4 times something going here, natural log 7, multiplied by the derivative of the input. So that's a format of the chain rule. Then this is the stuff going in those two blanks, t power 5 plus 3. Here and here. Phew, so we've got it, folks. That's the derivative of this line, just two chain rule issues to handle. I forgot to put a 1 on this one. We'll take the derivatives of those and just throw them into the numerators. We'll simplify, then we'll try, but if it doesn't, we'll just leave the answer right as it sits. So let's go and finalize. This is 1 over t times natural log 7 plus. On this one, I'm just going to bring all that stuff together. I'll go 7t minus 4 times 2 natural log 7 with a 1 in the numerator. Oh, not a 1 in the numerator. Let me try again. With a 7 in the numerator. Derivative of 7t goes to 7, and the minus 4 goes to 0 as a constant. That look all right to folks on that second term? Okay, one last one then. Here, there's going to be a minus from that negative 4. Down below, I'll just copy this as t power 3 plus 3. Or that's a 5. That was a miscopy. times the natural log of 7, then anyone see what the derivative should be where the red dot is right here? Exactly, we get our 5t power 4, then we just multiply it with that 4 right there. So all together, we should get a 20t power 4. How's that look to folks? Any questions on this step here? Yeah. Mhm. The 1/2 right here, and the -4 got combined with that -20. Let me take a look. Well, the 1/2 came from right here, and the constant multiple rule says if it's a constant multiplying, then you just copy this down. So 1/2 copies down, and we multiply by that derivative. And same kind of thing with that -4 right here. This just carried down to here as the constant multiple rule. But then when we differentiated the t power 5, the 5 came down, multiplying the -4, getting us down to that 20 right there. Does that make sense with those steps? Gotcha. Other questions at the moment? Okay, so this is like kind of the worst case of one you might see in the homework. And if we look at the homework at the moment, just because it's exciting and new, let's take a look at assignment 6. These are the kind of problems that we're getting into. Problems 2 and 3, nothing really special. Problem number 4 is suddenly a product rule, so we have to be careful. 5 is a chain rule, but so far no properties of logarithms. Problem number 6 does have a property of logarithms. The power 2 will come down, becoming a coefficient, and that one tiny step makes a massive amount of difference in how much work you're going to do on that one. Same issue with this one. If you see natural log of 1 over x, what you would really want to call this is natural log of x power -1. That's just doing exponent work. Then this becomes negative natural log x, and that's just way, way easier to differentiate. So its problem set starts off not really using properties of logarithms at first, but then suddenly they become massive. Like on problems 6 and 7 so far. Let me take a screenshot of this so it's not lost forever. I'll put it on the notes. Oh geez, that looks really ugly. I'll put it in the notes here and then clearly annotate. I just want to give a hint on these two problems because they look nice, but they're actually not nice. If you use properties of logarithms, it's much faster to get through these. But the one I want to take a look at is, let's see here, no properties of logarithms on that one. That one's just a quotient rule or a chain rule. But the ones we were doing are very similar to problem number 9. Without properties of logarithms, this one is a beast. So is 12. And we just did one that was similar to problem number 18 in our own work. That's the one I was looking for. So when you come up to problem number 18, yeah, it looks really bad, but it's really this process right here. So homework number 18, they're not the same, but this one is here because of that particular problem. Well, any questions so far, folks, on getting through these? Okay, well, we have a good 9 minutes, so I'll leave it up to the class. With 9 minutes of time, we could try to differentiate this function next. Does that sound all right to folks? Okay, let's give this one a try. This one's honestly a warm-up. And the warm-up is for this table right here. When we come back on Wednesday's class, we'll be going through this, practicing a few more derivatives before we go to section 3.7. So let's take a look at that row right there. Somehow, some way, the derivative of cosine is negative sine, but the derivative of the inverse function is not even written in terms of sines and cosines. It has an algebraic form. That's really, really unusual. And here's the idea of how it goes. We want the derivative of y equals cosine inverse x. First thing we should do is plot that. We want domains and ranges. So let's go over to Desmos. So there's cosine inverse x. Now keep in mind that inverse is a true inverse function. It's not an exponent. 1 over cosine x. is the secant function. It looks way, way different. So there's our secant function. Or excuse me, there's our cosine inverse function. Let's drop it on the notes. And here's the reason we need it. The moment we put that down on the notes, if y is defined to be cosine inverse of x, we can now say, well, the x itself goes from -1 to a +1. So those are the valid values for the domain x. The range values go from as low as 0 for cosine inverse and as high as 3.141, really exactly pi. So that's the domain and range. And with that on the table, we can run through differentiating that function there. So here's our first step. I'm going to copy down y equals cosine inverse of x. And just like what we've done at our first derivation for the derivative of log base a, we need to find a way to work with cosine inverse here. We'll find its inverse function is cosine and just take cosine of the left-hand side. So now it's cosine of y. Take cosine of the right-hand side. So now it's cosine of cosine inverse of x. And now any function compared with its inverse does that wonderful thing. It's an immediate cancellation. Whatever cosine inverse has done to x, cosine brings it right back. And so your right-hand side is just an x. Left-hand side is cosine of y. But we know how to differentiate both sides of that. And so now the next step is the true implicit differentiation. Any questions so far to this stage? Okay, so to differentiate this implicitly, I'll put this here. Let's use Leibniz to express this. We haven't done Leibniz in a while. For implicit differentiation, we'll do d dx of the whole left-hand side. And then d dx of the entire right-hand side, which was just x. So derivative of x is not so bad. We get a 1. Anyone recall what the derivative of cosine should be? Exactly. We'll get negative sine of y, but the chain rule says you have to multiply by the derivative of y. So it's times dy dx. So cosine was the outer function. We differentiate it first. There it is. Y goes inside. And because y is an inner function of x, we multiply by its derivative. We carry this up. We now have that the derivative of y with respect to x is -1 over sine y. That unfortunately was not quite there, because if we say it's a derivative with respect to x, the right-hand side has to involve x. So we still need a little bit of work to get through this, but it's not so bad. Any questions at all to get to this phase? Okay, when we did our first derivation, all we did was take a look at it. Where'd it go? Oh, there it is. We ended up right here and we said, that's not good enough because the right-hand side involves y, but we knew y is natural log a of x. So we just threw it in, canceled, and we were done. That one was kind of nice in a way. But trigonometric functions, they never seem to want to play super nice. And so even if I put cosine inverse right here, it's sine of cosine inverse, and I still have to simplify that. That's not an immediate cancellation. So that's why we do something instead. We'll use our best trigonometric identity we have, which goes sine squared y plus cosine squared of y equals 1. I'm going to try to solve for sine y and then just full on replace it. So you can isolate sine squared on this new identity. Sine squared of y is 1 minus cosine squared of y. Because it's a power 2, you can now square root both sides and get that sine y is either a positive or negative square root 1 minus cosine squared of y. Well, there's only two options here, positive or minus, but keep in mind, if y goes between 0 and pi, here's the unit circle diagram. Here's our rotation by y. And if we say sine y, no matter what that rotation by y was, it could go from here to here. Sine is the second coordinate, and the second coordinate is always positive between 0 and pi rotation. That means we're picking the positive sign. So we can say sine y equals root 1 minus cosine squared of y. And this is progress, but unfortunately, it's still not good enough. So I have a formula for sine y, and we can say dy dx is negative 1 over the square root of 1 minus cosine of y squared. It's the same conundrum, right? We just made the formula worse. It still has y inside there. Anyone see how to get y out on this next line? Pretty much, yeah. Right where we said here, y is cosine inverse x, or hang on, let me see, cosine y right here. I had a middle line. Let me write it in. Shouldn't have taken too many steps here. Cosine of y was equal to cosine of cosine inverse canceled and just gave us an x. But that's our second substitution. That cosine right there is really just an x squared. So the formula becomes the derivative of y with respect to x is negative 1 over the square root of 1 minus x squared, coming from right here, our third line. I put derivative operators around it, so that's why that step kind of just vanished out of thin air. But that's also the reason why we have these weird forms for the derivative of the inverse. They really come from here, and the result is simplifying the function you wanted. So all those weird formats for the inverse functions are really from the Pythagorean identities themselves. Well, we did it, folks. That's one derivative down, 5 more to go, and we'll practice those when we come back on Wednesday's class. Any questions at all with where this one ends? Okay, have a great night, folks, and I'll see you all on Wednesday's class. Any questions?
So where are we getting fuel mixed at the point where we used the previous bill class? Well, there's a kind of requesting price. Average over. What was that formula for?
That was for the definition of the derivative. Yeah, we were doing that in section 2.7 and 2.8.
And what would I use that on?
Anytime a problem asks you specifically to use the definition of derivative, it happened only on exam 1. It might happen on the final exam. But the moment we got into chapter 3, we just started using the differentiation formulas from then on.
Okay.
That makes sense?
And then I keep getting mixed up with the chain rules. Basically, just take the outer function and
Differentiate that one first.
Differentiate that and multiply by the inner function.
The derivative of the inner function. Exactly, yeah.
Cool. It makes a lot more sense. Thank you.
Awesome, glad to hear that.
I'm just wondering if I actually remembered this.
Remembered which one?
32.
I don't remember 32. Which section was it in?
4.
Section 4. Let me take a look with you.
Because I'm wondering if I actually did send her and not
Sender, sorry,
send this.
Oh, whether you sent it or not. Honestly, I'm not too sure, but I can leave a note.
Yeah,
I don't have my.
because I don't remember if I sent it or not. So I was like,
Gotcha. Sorry, I misunderstood your question this time.
because I was like, well, at least I have to turn it in eventually, but I'd rather it be something than nothing.
Gotcha.
And I'm more sad because it's actually probably my best work on my homework.
That's no good. Well, we'll take a look at it. Section 3.4. Yes.
Well, like 3.2.
3.2. Section 3.2 gets sent. in. I'll double check that. And I'll email you as soon as I find out.
And I'm just sure that my answer don't be them. Like that one's correct, that one's correct, that, not quite sure how to do this one.
This one is going to be quotient rule. together with product rule.
Good enough.
So when you go to start to differentiate that thing, it's gonna come out like this.
Basically what I just did. Oh, instead of a positive and negative.
Yeah, and the denominator is squared. But right here, we'll have to also use the product rule.
Oh, I got the denominator square from it.
Awesome.
And this because he is just gonna basically conform to one because.
True, but this whole thing, t sine t, once you put it here, you have to use a product rule on that step right
So
there.
the sine will become cosine.
Sine will become cosine, but
If you differentiate t sine t, you now have to do this thing to it.
It sounds all very complicated.
because has a product right here, you need to use a product rule on that derivative as well.
So great, now I have one plus cosine plus sin again,
They'll go one here, sine t.
times
and then
sin,
t,
times sine,
And then cosine.
and then cosine. So that's
Yeah.
where okay, that explains why there's more than like.
Yeah, there's gonna be lots of different.
Because there's
terms
like
there.
two cosines and then there's one sin. I was like, okay, that makes sense.
Gotcha. Question over here?
Yeah. So I'm doing 3.4, this is 10, then this is the function. So I figured I would take the square root of it, right?
Yeah, that one would be, is that 3?
Yeah.
Gotcha, that would be a cube root of that one.
Yeah, and then the chain rule,
Mhm.
right? So I bring that out, put that in, take the derivative of this. And am I doing that all over 1? Right? So it'd be 1 over this.
I think you're on the right track, but there's one additional step I would take on this when you're simplifying. Your f of x, you have it reduced to 1 over x squared, and it goes already
Minus
forgot,
1.
minus 1 to power 1/3.
Okay.
But because the formula that we want to use goes ddx of x power n is x power n minus 1. What we really need is your base, that whole thing to be up in the numerator. So it could simplify even more by making it x squared minus 1. If we flip to the numerator, this becomes a negative 1/3 as an exponent.
And I wouldn't have a denominator. It would just be like that.
Right, well, I mean, the negative 1/3 is gonna come down, so there's still kind of like a denominator from this. But now we go to use the power rule, your n is that negative 1/3 coming down. So this is the outer. And then by chain rule, like you're saying, this one will be the inner.
Okay. Minus. Okay, thank you.
Yeah, you bet. So your set is really gonna kind of look like this, negative 1/3. You have to subtract 1 from this,
Mhm.
that's really -3 over 3,
So negative 4/3.
exactly.
Okay,
So that's pretty much your set of the template.
right. Okay. I think that's where I was going wrong. I didn't put it in the numerator.
Gotcha.
Okay,
And I think I finally understand your question. If you want to keep that as a negative exponent, you will have a numerator. But if you want to force that as a positive 1/3, the whole thing would turn into a denominator.
right.
But that's all kind of up to you. I'm not too worried about
Okay,
it.
I can leave that as a.
Yeah, I would be completely fine with that.
Okay.
I think a good rule of thumb is if you're taking more than 3 steps in algebra, simplifying, you probably took too many. It's okay to stop earlier.
Okay, perfect. Thank you.
Yep, you bet.